Now in continuation of nucleophilic substitution, the next reaction we're gonna see is nucleophilic aromatic substitution. So here it is a nucleophilic aromatic substitution, which is known as NAR, where AR stands for aromatic. Now what is the condition? The condition of nucleophilic aromatic substitution is, we know aromatic compounds we already have seen in general organic chemistry. So in organic compound, if we take the example of benzene, generally we will be using here benzene only. So benzene have the condition is halogen and NO2 must be at ortho and para to each other. So we have halogen and we have NO2. So they must be at either ortho and para. The relative position of each other should be ortho and para. Now if we know that here chlorine is a good leaving group, so chloride ion is a good leaving group. So we have a solution. Let's take an example when the NO2 and halogen are at ortho position, okay, the para position. They are relative to each other, para position. Okay, now when only a single NO2 we have, so we will be requiring the OH minus ion obviously to replace the chloride ion. In that case, we will need the concentration of OH minus very high. pH 14 means we are using a very strong base, very strong base we are using now. Now the temperature should also be very high, because it is not easy to replace the substitute of chloride due to resonance. But as we know, the pH should be high and temperature also should be 140 degrees Celsius when NO2 group is present at the relative para position of chlorine. Okay, so that gonna replace chlorine, and here there will be OH. Now if you see when we replace one of the ortho position by NO2 and one of the para position by that NO2. Now in that case we need a little bit less temperature. We need 100 degrees Celsius. It works on 100 degrees Celsius, and it also works when pH is 10. Up to when pH is 10, it's again OH minus is able to replace the chlorine. So here we know that nucleophilic aromatic substitution is not a general substitution reaction. We need external reaction conditions, like pH should be very high. pH high means the solution should be very basic. That's why this is OH minus concentration is there, and the OH minus is replacing chloride ion. Now again when pH is 10, then OH minus is replacing again, and when temperature is 100 degrees, because they are supporting agent. The NO2 here, it's supporting to the reaction. We have already seen the aromatic reactions, that how it is supporting. Now we're gonna see its detail in mechanism also. Let's see the third condition, when all the ortho and para portion are occupied by NO2, then chlorine can be then it can be replaced at pH 7. Okay, at general temperature it could be replaced. So now when it replaces, it forms this. So this is known as, this reaction is this is known as picric acid. So this is the formation of picric acid also. Its pK is 0.5. It is a very, its pK is 0.5 and it is a picric acid. So how picric acid is formed? When ortho meta para, the chloride and the nitrogen group is at present and ortho and para, and chlorine is there. So at pH, neutral pH, the reaction could also be proceed. Now if we go further, if we go in detailed mechanism here, its mechanism. So here we know that when the RDS and the reaction conditions are completed, then it is aromatic substitution. So OH gonna replace chlorine. So OH will first attack here. Okay, now we know that that carbon can have maximum 4 bonds. So when OH will attack, this double bond will shift towards here. So we know that this benzene ring is destroying its aromaticity. Okay, its aromaticity here. So the reaction condition, all the it is using to proceed the very first step, because it is a very time taking step. It could be it is the most slowest step, because it is it is taking a lot of time, because the energy graph, the energy of product is very less as compared to energy of reactant. So we need to supply energy here, and we need to take time. That's why it is a RDS step, rate determining step, or we can say the slowest step in the reaction. Now this type, Then intermediate form, this is known as Mishenheimer complex. Okay, Mishenheimer complex. Now in Mishenheimer complex, what it is that when we know that this gonna again coming in the resonance, in the further resonating structure, there will be negative charge in this side, then negative charge will be on this side. So that's how NO2 is supporting the reaction, and the nitride group, NO2 group, is supporting the reaction. If it is as a ortho position, if we see if comes in the ortho position NO2, then also we can see that it is also supporting, because the negative charge gonna revolve from ortho para then again ortho. So if we add more NO2 at ortho position, so it will be more stabilizing the reactant. So reaction will be relatively fast, or it will be needed relatively less energy. So that's why we have seen that when we add more NO2 group to the ortho position, so we need a less temperature, we need a less activation energy. Okay, here we use 140 degree, and due to decreasing the aromaticity, the nucleophilicity, we have need the pH very high, because it is intensifying the nucleophilicity, and that's why it is able to replace. And here it is we need a relatively less intensified nucleophilicity, that's why we are using the pH 10 also here. So this is known as elimination. So this is the addition step. The first step, which is RDS, is addition step, addition of OH minus hydroxide ion to that chlorobenzene. That para position NO2 is attached. Now if we see the second step is known as elementary step. Now in elementary step, that OH and NO2, that we have replaced the OH by then again when negative charge come here, the negative charge goes back, then Cl chloride ion will come out, because here the Cl is a good leaving group relative to OH. So if you see the last step, in our last step, if you see that this will be our negative charge, and the reaction this Cl and OH, and this is a bond, and here this is, now here we have this and this, so this double bond and this double bond. So when the reaction will go in the last step, so there is a possibility the chloride can ion, OH can ion. So we have seen the chloride, when chlorine will come out, it will form Cl minus, when OH will come out, it will form OH minus. So it's a conjugate base, so its acid is HCl and its acid is H2O. So we know stronger the acid, good the leaving group. So here chloride is a good leaving group, so here Cl minus comes out of the reaction. Now if we see the characteristic of the reaction, so rate is directly proportional to the concentration of halide as well as concentration of nucleophile. So here it is a second order, and the first step is also elementary step. Now in elementary, order equals to molecularity, that is coming out of 2. So this is RDS, and here these both concentration matters, so that's why it is a second order reaction. Now if we see further that the intermediate, this is the intermediate of the reaction, this is intermediate. Now intermediate is the carbon ion, here carbon ion is the intermediate, so carbon ion is the intermediate. So when carbon ion is the intermediate, so more stable the intermediate, okay, stable the intermediate, so faster will be the reaction, faster will be the reaction. So now here if you see that if we have these four options, like if we have to compare the rate of the reaction, if we have to compare which will go fast and which will go slow in the same reaction condition, so we know that this will be the intermediate form. Okay, this is the intermediate form. Now we know that the removal of HF minus is the last step, but in the intermediate step there is a negative charge which is revolving around ortho para and again ortho position. So more the stable the intermediate. So what could make the intermediate stable? We have NO2 same. Okay, so NO2 is same. The differentiating element is here halogens. One have fluorine, one have chlorine, one have bromine, and one have iodine. So we know that in that case fluorine could show only minus I effect. It is not able to show plus R plus M effect. So it is only able to show minus I effect. So more the minus I effect stable, more the minus I effect. So if we compare here, more minus I effect, okay, more carbon ion will be stable, that we have seen again already in GeoC. We know that minus I effect stabilize the negative charge. Okay, so it is pulling electron, so it is stabilizing the negative charge, or it is de-intensifying the negative charge. When it is de-intensifying the negative charge, then it is making stable. So here we know the order of the reaction, the rate of the reaction will be the fastest in case of fluoride, then chlorine, then bromine, then iodine.